Imagine for a second that you decide, you're going to start a brand new workout routine.
Always a good idea in theory.
Right, exactly. So you head to the gym, you pick up some moderately heavy dumbbells, and you do a set of bicep curls,
Okay.
and you feel that familiar burn, right? And maybe you've got a little soreness the next day.
Yeah, the classic delayed onset muscle soreness.
Exactly. And for most of us, that soreness is a signal of growth. I mean, the muscle heals, it builds back a little bit stronger, and you ultimately get healthier.
That's the normal physiological response, yeah.
But imagine if, because of a single, a microscopic typo hidden deep inside your DNA, that normal healing process just simply didn't exist.
Oh, wow.
Right. Instead of building back stronger, those bicep curls you just did were permanently destroying your muscle tissue.
Just tearing it down with no rebuild.
Exactly.
Yeah.
Flooding your kidneys with toxic proteins and basically accelerating your path to a wheelchair.
It completely flips our intuitive understanding of health totally on its head.
It really does.
I mean, you think you are doing the right thing for your body, but your underlying molecular machinery is essentially betraying you.
Betraying you, yes. And today we are bringing you into the really murky, high-stakes world of limb-girdle muscular dystrophies, or LGMDs, as they're known.
It is a massive, incredibly complex topic.
It really is. We are unpacking a staggeringly dense but fascinating medical review by Dr. Tiran Lulak.
A truly comprehensive piece of work.
Oh, absolutely. And our mission for this deep dive today is to really figure out how these terrifyingly complex genetic diseases actually work.
We have to break it all down.
Right. We're going to look at the microscopic anatomy of a dying muscle cell. We're going to trace the chaotic history of how doctors tried to name a disease that just kept outsmarting them.
The history is wild, by the way.
Oh, we are getting into it. And we'll dig into the bleeding edge reality of gene therapy, where the quest for a cure has literally life or death consequences.
So to really grasp what you are dealing with when you hear that term, limb-girdle muscular dystrophy, we should probably break down the name itself first.
Yeah, let's start there. What does that actually mean?
Well, it's an umbrella term. It covers a genetically heterogeneous group of skeletal muscle disorders.
Heterogeneous meaning like a whole bunch of different causes.
Exactly. Lots of different genetic causes, but they present somewhat similarly. They are inherited autosomally.
Okay, autosomally. Break that down for us.
Right, so that means the genetic mutation isn't linked to the X or Y sex chromosomes.
So it's not a sex-linked thing.
No, it affects men and women equally.
Got it.
And clinically, the absolute hallmark is progressive weakness in the proximal muscles.
Proximal meaning the ones close to the core.
Yes, the muscles closest to the center of your body. Specifically, we're talking about the pelvic girdle around your hips and the shoulder girdle.
Okay, so the muscles you use to, say, stand up from a really low couch.
Yes.
Or reach up and grab a heavy box off a high shelf in the garage.
Exactly, those big central power-generating muscles.
Okay, but before we get into the cellular destruction, because we are going to go deep into that, I really want to talk about how incredibly difficult it has been for the medical community to even define what this disease is.
Oh, it's been a nightmare.
Right, because historically, LGMD wasn't a specific diagnosis at all. It was more like a bucket.
Massive, just overflowing catch-all bucket.
Yeah.
If we go back to 1953, a researcher named Stevenson actually coined the term.
Okay.
And then the very next year, in 1954, Walton and Nattrass really formalized it in the medical literature.
But the thing is, they weren't discovering a single new disease, were they?
No, not at all. They were looking at a spectrum of patients who had progressive muscle weakness,
Yeah.
but who clearly just didn't fit into the other established category.
Right, it was like an exclusion thing. Well, they don't have this and they don't have that.
Exactly.
Mm-hmm.
They knew these patients weren't Duchenne muscular dystrophy patients, for instance.
Because Duchenne is linked to the X chromosome, right?
Right. Duchenne almost exclusively affects young boys. So these patients didn't fit that profile.
Okay.
And they also knew they weren't congenital muscular dystrophies.
Congenital meaning born with it.
Right. Those babies are born with severe weakness. But with LGMD, that is the absolute crucial dividing line.
This is such an important point.
It really is.
Mm-hmm.
To be classified as having an LGMD, the patient must have achieved independent walking at some point in their life.
Okay, so they had to have hit that milestone.
Yes. Whether they walked normally until they were 3 years old, or 30, or even 60.
Wow, even 60.
Oh, absolutely. But that developmental milestone of independent walking had to be reached before the weakness eventually took it away.
So the medical field basically had this giant other category, the limb girdle bucket.
Exactly. And for a few decades, honestly, that bucket held up pretty well.
Because they just didn't have the tools to look any closer.
Right. If you had proximal weakness and you didn't fit anywhere else, the doctor would just say you have LGMD.
But then the genetics revolution happens in the 1990s.
And everything changed.
Yeah. Scientists started looking into that limb girdle bucket and realizing it was filled with dozens of completely unrelated genetic catastrophes.
Which just happened to look identical on the outside.
It's wild. So in 1995, the European Neuromuscular Center realizes this old system is totally useless.
They needed a way to organize this massive explosion of genetic data.
Right, so they created this alphanumeric naming system, which at the time probably seemed very logical.
Oh, it made perfect sense on paper. If the disease was autosomal dominant, meaning you only need one faulty copy of the gene from one parent to get sick,
Oh,
and they called it LGMD1,
okay.
and if it was autosomal recessive, meaning you need a faulty copy from both parents, they called it LGMD2.
And then the way the text explains it, they just appended a letter of the alphabet based on the chronological order of when the gene mutation was discovered.
Right, so you'd get LGMD2A, then LGMD2B, LGMD2C.
Which sounds like a very tidy, logical way to organize a filing cabinet.
Until your filing cabinet encounters the sheer speed of modern gene sequencing.
Right, because they literally ran out of letters.
It's true. The pace of discovery was so relentless that by 2016, researchers had identified so many recessive subtypes that they hit LGMD2Z.
I mean, it's just incredible.
They literally ran out of the English alphabet.
You build a system to catalog human disease, and human biology is just so wildly complex that you exhaust the entire alphabet.
Yeah, the system broke. They had to scrap the whole thing.
But what did they do?
They had to call a massive international workshop in 2017 to invent a new system that wouldn't break down so easily.
Okay, so what's the new nomenclature?
Now, we use a much more scalable system. We use LGMDD for dominant forms and LGMDR for recessive forms.
And then just a number.
Exactly, followed simply by a sequential number. So today, according to Dr. Liulek's review, we are dealing with 5 dominant types, D1 through D5,
Okay.
and a staggering 29 recessive types, R1 through R29.
Which I think raises a really important point for anyone actually navigating this diagnosis.
That's-
Well, does knowing if you have a D for dominant or an R for recessive actually tell you anything about what you're going to experience? Or is that just trivia for the geneticists?
Oh, no, it's deeply clinically relevant. It maps directly to the severity of the disease.
Okay, so how do they differ?
Autosomal dominant diseases, the D types,
Mm-hmm.
typically appear much later in life.
So, like, what age range?
We are talking adolescence
Hmm.
to late adulthood. And the weakness progresses relatively slowly. It's generally milder.
Okay.
The recessive forms, the R types, are a completely different animal,
More severe.
much more severe. They usually have a much earlier onset, very often in early childhood.
Oh, wow. And the muscle destruction is faster.
Yes, the muscle destruction in the recessive types is drastically more severe. And you can actually measure that severity with a simple blood test.
Right, the test looking for creatine kinase.
Exactly. Creatine kinase, or CK.
So what exactly is CK doing in a normal, healthy body?
Well, creatine kinase is an enzyme that normally lives inside your muscle cells. Its job is to help generate ATP, which is the fundamental energy currency of the cell.
Right, for when you need to run or jump or lift something.
Yes, when your muscles need a sudden burst of power. Now, in a healthy muscle, the CK stays inside the cell where it belongs.
Because the cell wall is intact.
Exactly. But when the outer membrane of the muscle cell tears open and the cell dies, all of its contents just spill out.
They spill into the surrounding tissue.
Right. And eventually, all that cellular debris washes into the bloodstream.
So measuring CK in the blood is essentially taking a death toll of muscle cells.
That's a grim but incredibly accurate way to put it.
And in these recessive LGMDs, those CK levels are just phenomenally higher.
Unbelievably high, sometimes tens of thousands of units per liter.
Compared to what? What's a normal level?
A normal level is maybe 1 or 200.
Oh my God.
Yeah. So when you see a number in the tens of thousands, it tells you the muscle is actively, rapidly breaking down, which for the patient translates to a much faster loss of mobility.
So the genetic categorization, whether it's D or R, tells us a lot about the timeline.
Yes.
But I want to look at the physical reality of the disease because we call it muscle weakness, but that phrase feels way, way too simple for what is actually happening.
It definitely masks the complexity of the symptoms.
Right. Like a patient might start noticing they are waddling when they walk.
The waddling gait is classic, and it happens for a very specific anatomical reason.
Break that down for us.
It happens because the gluteus medius muscle becomes weak.
That's the muscle on the side of your hip, yeah?
Exactly. It's the muscle that stabilizes your pelvis when you lift one foot off the ground.
Okay, so when you take a step.
Right.
Okay.
Without that stabilization, the pelvis drops on the swinging side.
Hmm.
And to compensate, the body has to throw its weight over the weakened hip just to stay upright.
Which creates that waddle. And you also see hyperlordosis, right? That deep, exaggerated arch in the lower back.
Yes, that's another major compensation mechanism. The hip extensors weaken.
So those are the muscles in the back of the leg and the glutes.
Right. So the patient essentially has to thrust their belly forward and lean their upper body backward.
Just to keep their center of gravity over their legs.
Exactly. Otherwise, they would just fall flat on their face.
It's amazing how the body tries to adapt, but the clinical presentation doesn't stop at the muscles.
No, it doesn't.
And this is where the biology gets truly fascinating and honestly devastating.
You're talking about the extramuscular manifestations.
Yes. Some of these subtypes have severe symptoms that you would never intuitively associate with a muscle disease.
It really catches people off guard.
Skin blistering is the one that really stopped me in my tracks when reading this source.
Oh, yes. That's a very specific phenomenon.
There is a specific subtype, LGMD-R17, where patients develop epidermolysis bullosa simplex, which means their skin becomes so incredibly fragile that mild friction, like literally just the rubbing of a shoe or the seam of a shirt, causes severe, painful blisters.
It's brutal.
And then, in the collagen VI-related dystrophies, patients develop keloids.
Right, which are these thick, raised, aggressively growing scars.
Along with this rough, bumpy skin condition called follicular hyperkeratosis.
Yeah.
But, I mean, why, if this is a muscle disease, why are some patients getting skin blisters or keloids?
It's such a good question. To understand why a muscle disease causes skin blisters, we have to stop thinking of our bodies as a collection of separate, completely disconnected organs.
Okay, so it's all connected.
It is. We have to look at the structural proteins that actually build our cells.
Right.
So in that subtype you mentioned, LGMDR17, the genetic mutation breaks a specific protein called plectin.
And plectin acts like a microscopic scaffolding pole,
Well,
right?
basically, yes.
Yeah.
It's a massive cross-linking protein. Inside your cells, you have a cytoskeleton.
A skeleton for the cell.
Right. It's a network of fibers that gives the cell its shape and its mechanical strength. Plectin ties those fibers together and anchors them to the outer cell membrane.
Okay, I'm with you.
Now, plectin is heavily utilized in muscle tissue because muscle undergoes a massive amount of mechanical stress every time you move.
Makes sense.
When the plectin is defective due to that mutation, the muscle cell essentially collapses under the strain of movement and it dies.
But here's the kicker, plectin isn't only in muscle tissue.
Exactly. It's also a absolutely critical structural component of the skin cells in your epidermis.
Wow.
So the exact same structural collapse happens there. The basal cells of the skin literally tear apart from the underlying layers at the slightest mechanical friction.
Which fills with fluid and creates a blister.
Yes. The genetic typo doesn't care what organ it's in. If the tissue relies on that specific protein to function, that tissue is going to fail.
That is just mind-blowing, and we see this incredibly clearly with the heart and the lungs, too, according to the text.
Oh, yes. Dilated cardiomyopathy is a massive risk in many subtypes.
Which is where the heart muscle stretches out, becomes thin, and just fails to pump effectively.
Right. And respiratory insufficiency is another huge issue because the diaphragm, which controls your breathing, is a skeletal muscle, and it wastes away just like the muscles in the legs.
That's why managing this disease isn't just about going to physical therapy for your legs. Cardiopulmonary surveillance is the absolute cornerstone of keeping these patients alive.
It's a full-body management strategy. You have to monitor the heart and lungs constantly.
And the weirdness of how this disease presents goes even further. We naturally assume, weakness will be symmetric.
Like affecting both shoulders equally or both hips.
Right. But the text highlights that some subtypes, like R2 and R12, cause highly asymmetric weakness.
It can be very lopsided.
One calf muscle might be severely wasted away, while the other looks relatively normal.
It really complicates the diagnostic picture. Or consider the patients who don't present with persistent weakness at all in the beginning.
Wait, no weakness, but it's a muscular dystrophy.
Right, but initially, they present with what looks like a metabolic disorder.
Okay, so what does that look like?
They go to the doctor complaining of severe muscle cramping during exercise,
Mm.
or sudden, acute episodes of rhabdomyolysis.
Oh, let's unpack rhabdomyolysis, because reading about that cascade in the text was terrifying.
It is a medical emergency.
So you push yourself a little too hard physically, maybe you're running or lifting heavy,
Okay.
but instead of just getting sore, your muscle tissue undergoes massive, sudden necrosis. It just dies and dissolves.
The cells essentially burst.
Right.
Yeah.
And the real danger isn't just the muscle loss, as bad as that is, it's what happens to the kidneys.
Yes. The systemic effect is where it gets life-threatening. When that muscle tissue breaks down, a protein called myoglobin is released into the bloodstream in massive quantities.
And myoglobin is normally good, right? It's the protein that stores oxygen in your muscles.
Normally, yes, it's vital. But when it's dumped into the blood in huge amounts and reaches the kidneys, it is highly toxic to the renal tubules.
Because the kidneys are the body's filtration system,
Right.
and suddenly they are clogged with this dense, dark protein.
And this leads to a very visible symptom. The patient will literally urinate what looks like dark tea or cola.
Oh, wow.
That is myoglobinuria.
And if it isn't treated immediately, like with aggressive intravenous fluids to flush the kidneys, it causes acute tubular necrosis.
The kidneys shut down.
And the patient goes into renal failure, all because of a hidden genetic defect in their muscle membranes.
It's a stark reminder of how interconnected our systems are.
So, with 34 different subtypes presenting as everything from skin blisters to kidney failure to asymmetric calf wasting, I mean, it is impossible for a clinician to just memorize a checklist of symptoms.
You absolutely cannot just memorize it.
Yeah.
You have to group these diseases functionally.
By what is actually breaking down at the cellular level.
Exactly. You have to look at the mechanism of the destruction.
So let's do that. Let's look at the molecular mechanisms.
Right.
Let's start with the largest and most prevalent groups, starting with the single most common subtype in the United States and Northern Europe.
That would be calpanopathy.
Right. Which covers the recessive R1 and the dominant D4.
So calpanopathy is caused by mutations in the CAPN3 gene.
Okay, the CAPN3 gene, and what does that do?
It produces an enzyme called calpain-3. Now, calpain-3 is a protease,
Which means...
meaning its primary job is to chop up other proteins.
Okay, so it's like molecular scissors.
Yes. And inside the muscle cell, it is tightly bound to a gigantic structural protein called titin.
And titin is actually the largest protein in the human body, right?
It is. It acts like a giant molecular spring inside the muscle fiber.
Giving it that elasticity.
Right. And as that spring stretches and contracts during normal movement, the muscle takes microscopic damage.
Just normal wear and tear.
Exactly. So calpain-3 sits on titin and essentially acts as the maintenance crew.
Okay, I love this analogy.
When proteins get damaged during exercise, calpain-3 cleaves them away, it chops them up so they can be replaced.
And that allows the muscle to remodel and adapt to the stress.
Precisely. But when calpain-3 is mutated and non-functional,
The maintenance crew is on strike.
yes, the damaged proteins just accumulate, they pile up, the muscle becomes choked with cellular garbage, it fails to adapt to stress, and eventually it just dies.
Wow. And clinically, calpanopathy usually starts attacking the hip extensors and the knee flexors.
Yes, those are the typical early targets.
But there is a very distinct visual sign on the upper body that the text talks about: scapular winging.
Scapular winging is very prominent in this subtype.
Explain what that actually looks like.
Well, the muscles that anchor the shoulder blade, the scapula to the rib cage, like the serratus anterior and the rhomboids,
Right, those stabilizing muscles in the upper back.
they become profoundly weak.
Hmm.
So when the patient pushes their arms forward against a wall, the shoulder blades basically detach from the back,
And they stick out sharply.
like wings.
Right. What's wild to me is that scapular winging makes calpanopathy look nearly identical to a completely unrelated disease.
Yes, facioscapulohumeral dystrophy, or FSHD.
So you have this massive diagnostic overlap where doctors might be looking at two totally different root causes.
It happens all the time.
But let's shift to another group of LGMDs where the mechanism of destruction is completely different.
Okay, what's next?
The muscular dystrophies with defective membrane repair.
This is a fascinating group. This includes LGMDR2, which is dysferlinopathy.
And R12 and noctuminopathy 5.
Right. To really understand this one, you have to visualize the outer wall of the muscle cell, which is called the sarcolemma.
The sarcolemma. Okay, so every time you move, whether you are walking to the fridge or, sprinting down a track, that sarcolemma is subjected to immense shearing forces.
Incredible stress.
And it constantly suffers microscopic tears.
Right.
Little holes just pop open in the cell wall.
Which sounds bad, But in a healthy cell, those holes are an emergency, but a completely manageable one.
How does the cell manage it?
When a tear occurs, calcium from outside the cell begins rushing in through the hole.
Because there's a higher concentration outside.
Exactly. And that sudden spike in local calcium inside the cell acts as a sort of alarm bell.
Okay, the alarm rings, then what?
It triggers specific proteins, primarily dysferlin, to grab nearby vesicles.
Vesicles are like little bubbles, right?
Yes, little bubbles of spare membrane material. Dysferlin grabs these bubbles and rushes them to the tear.
They act like molecular paramedics.
Exactly. They jam those spare membrane bubbles into the hole, they fuse them together, and they patch the leak almost instantly.
It's an incredible system. But in patients with R2 or R12, the dysferlin or the anoctamin 5 proteins are mutated.
Right. They either don't exist at all, or they're the wrong shape to do the job.
So the microtears happen, the calcium rushes in, but the paramedics never arrive.
The hole just stays open.
And the calcium just continues to flood the interior of the cell.
And that is catastrophic. Too much calcium inside a cell is a death sentence.
Why? What does the calcium do?
It hyperactivates destructive enzymes, it overloads the mitochondria, and it triggers a self-destruct sequence. The muscle fiber literally digests itself.
Wow. And this specific mechanism, this lack of repair, explains one of the most heartbreaking clinical paradoxes we see in the literature.
You're talking about the exercise paradox.
Yes. There was a well-documented cohort of teenagers with dysferlinopathy. And naturally, they were told by everyone that exercise is good for you. So many of them engaged in heavy sports and athletics.
As any active teenager would.
But the ones who exercised more actually deteriorated faster.
It's tragic.
They experienced an earlier onset of severe weakness, and they ended up in wheelchairs sooner than the patients who were more sedentary.
Yeah.
It feels incredibly cruel. You do exactly what society tells you to do to stay healthy, and you are actively destroying your body.
But biochemically, when you understand the mechanism, it makes perfect devastating sense.
Because of the microtears.
Exactly. Heavy exercise creates vastly more microtears in the sarcolemma. Because their cells lack that dysferlin patch kit, every single workout was basically a mass casualty event for their muscle fibers.
They were just shredding their muscles with no way to heal.
Right.
And this defective membrane repair group is also famous for producing bizarre, highly localized muscle wasting.
Yes, the atrophy patterns are very
You don't just get
unique.
general
You don't just get
weakness. You
general
get selective
weakness. You
atrophy
get selective
that
atrophy
leaves
that leaves adjacent muscles
Which
completely
creates
untouched.
these very
Which
unnatural
creates these very
contours on the
unnatural
limb.
contours
And
on the
doctors
limbs.
historically
And
gave
doctors
these very
historically gave these very
French
descriptive
names to them,
French
right?
names
Yes,
to
like
them,
the
right?
voodoo biceps.
Which means a distinct bulge on the biceps muscle.
Or the diamond on the quadriceps.
Quadriceps.
It's fascinating, but it also blurs the lines of our established categories again. We said LGMD targets the proximal muscles, the hips and shoulders.
At the
But
definition, yes.
mutations in these exact same genes, dysferlin and anoctamin 5, can cause a completely different disease called
Myoshi
myopathy.
myopathy targets
The distal muscle.
The distal muscle, so farther away from the core.
Absolutely shreds
the calf muscle, specifically the gastrocnemius and the soleus.
To the point where patients lose the ability to stand on their tiptoes.
It is the identical
It is the identical genetic
breaking
typo,
the identical
breaking the identical membrane repair
But for some
process.
reason we still
But
don't
for
fully
some reason we still don't fully understand. It decides to destroy the lower leg instead of the hip.
That is
It's a
wild.
humbling
It's a
reminder
humbling reminder of how much we still have to learn about tissue specificity. Why does the typo care where it is? We don't really know.
Well, let's move to the largest functional group
detailed in the
the
text.
alpha dystroglycanopathies.
Okay, a
There
huge
are
group.
11
There are
subtypes
11
in this family.
subtypes in this family, the most notable being LGMDR9, which is linked to a gene called FKRP.
And with the alpha
Right. And with the alpha dystroglycanopathies, the problem isn't patching holes in the wall like
What's
we
the
just talked
problem
about.
here?
What's the problem here?
The problem is anchoring the wall to the outside
so
world.
imagine the
Okay,
muscle
so
cell
imagine
as
the
a
muscle
balloon.
cell as a
Okay,
balloon.
Inside
Okay,
the balloon,
balloon.
you have
Inside the balloon, you have the cytoskeleton, the structural framework. Outside the balloon, you have the extracellular matrix.
Which is a dense web of collagen and connective tissue that basically holds all the cells together in a functioning
Right.
muscle belly.
And for the
Right.
muscle to generate
And for the muscle to generate force without tearing the balloon
the
apart,
inside skeleton
has to be physically bolted to the outside matrix.
Yes, structurally anchored.
And that bolt is a massive protein complex.
right across the cell membrane,
And a key piece of that bolt is alpha dystroglycan.
which sits on the outer surface of the cell, reaching out to grab onto the matrix.
Right. But, and this is the crucial part, alpha dystroglycan can't just grab the matrix on its own.
It needs help.
It needs to be heavily modified. Specifically, it needs a long chain of complex sugar molecules attached to it.
The sugar coating process.
Exactly. This process is chemically called glycosylation.
So the enzymes in the cell act like a factory assembly line, carefully attaching these specific sugar branches to the alpha-dystroglycan protein.
And those sugar branches act as the actual Velcro that sticks to the extracellular matrix.
So in the alpha-dystroglycanopathies, the actual alpha-dystroglycan protein itself is perfectly fine.
Yes, the protein is normal. The genetic mutations, like the FKRP mutation, break the enzymes on the assembly line.
Ah, so the factory fails to attach the sugars.
Yes, so the protein makes it to the surface of the cell, but it's completely bald.
It has no Velcro.
Exactly. It reaches out to the extracellular matrix, but there's no grip.
So the cell essentially detaches from its surroundings.
Yes, and every time the muscle contracts, the shear force rips the unanchored membrane apart, which leads to profound muscle necrosis.
And crucially, the text points out that this alpha-dystroglycan anchor isn't exclusive to skeletal muscle.
Right, this goes right back to the multitasking proteins we talked about with the skin blisters earlier.
Right, so where else is this anchor used?
Alpha-dystroglycan is absolutely vital in the central nervous system.
In the brain.
Yes, it helps guide neurons to their proper places during fetal brain development, and it's also critical in the retina of the eye.
Wow. So patients with severe alpha-dystroglycanopathies don't just suffer from muscle weakness.
No, they often present with severe structural brain malformations.
Like lissencephaly.
Right, where the brain lacks its normal folds and grooves, it's smooth, along with profound cognitive impairment, seizures, and severe eye abnormalities.
It's devastating. And finally, just to round out the major groups, we have the sarcoglycanopathies.
Which covers LGMD R3, R4, R5, and R6.
So what's breaking here?
The sarcoglycan complex is another crucial part of that exact same anchoring bolt we just discussed.
Okay, the same bolt structure.
Yes. It's a cluster of 4 distinct proteins that sit embedded in the cell membrane, stabilizing the whole dystroglycan connection.
I think of it like 4 pillars holding up a bridge.
That's a perfect way to visualize it.
If a mutation knocks out the gene for just one of those pillars, the entire bridge destabilizes. The whole complex falls apart.
Exactly. And clinically, these sarcoglycanopathies are incredibly severe.
They closely mimic Duchenne muscular dystrophy, right?
Very closely. Onset is usually in early childhood. The progression is incredibly rapid.
And you see that calf enlargement too.
Yes, pseudohypertrophy, where the dying muscle is replaced by fat and scar tissue, making the calf look artificially huge.
Which is such a confusing visual symptom.
And tragically, these children frequently lose the ability to walk entirely by their teenage years.
Okay, so we have all these groups: calopinopathies mimicking FSHD, sarcoglycanopathies mimicking Duchenne, membrane repair defects blurring into Miyoshi myopathy.
It's a lot.
I mean, the clinical overlap is just a complete nightmare.
It really is.
If you are a neurologist sitting in a clinic, how do you actually diagnose this? How do you know which of the 34 genetic typos is actively destroying your patient's muscles?
Well, historically, diagnosing LGMD was a pretty brutal, inexact science.
Because the gold standard used to be the muscle biopsy.
Yes.
Which literally means surgically cutting a chunk of muscle out of the patient's body.
Yes. Taking a physical piece of tissue, usually from the thigh or the shoulder, freezing it in liquid nitrogen, and slicing it into sections a few microns thick to look at under a microscope.
But the pathologist looking at that slide wasn't seeing the broken genes, right?
No, they couldn't see the genetic typo.
They were just seeing the aftermath of the war.
Exactly. They would see fibrosis, which is heavy scar tissue.
Okay.
They would see fatty replacement, where fat cells had literally taken over the empty space left by dead muscle fibers.
Just filling the void.
Right. Or they might see centralized nuclei, which is a sign the muscle is desperately trying and failing to regenerate.
It sounds incredibly vague.
It was, and sometimes they would see features that actively misled them.
Wait, really? Give me an example.
Well, for instance, early in the course of LGMD1, calpanopathy, the biopsy often shows prominent eosinophilic infiltrates.
Eosinophils. Okay, let's explain that. Eosinophils are a type of white blood cell, right?
Yes. They are part of your immune system.
Yeah.
Usually they're involved in fighting off parasites or driving allergic reactions.
Okay, so when a pathologist sees white blood cells swarming a muscle tissue slide...
Their immediate perfectly logical conclusion is that the immune system is actively attacking the muscle.
Oh, no. So they misdiagnose it.
Right, they diagnosed the patient with an inflammatory myopathy, like eosinophilic myositis.
Which is a massive problem.
A huge problem.
Because the treatment for an inflammatory autoimmune disease is to hammer the patient with high-dose corticosteroids or immunosuppressants.
Essentially shut the immune system down.
But the patient doesn't have an autoimmune disease.
No, they have a structural genetic defect.
So they are subjected to months or even years of toxic steroid treatments.
Gaining weight, losing bone density, risking diabetes, and severe infections.
All while their actual muscle disease continues to progress completely unchecked.
It's a tragic clinical trap. The biopsy was essentially looking at a collapsed building and trying to guess if it was a tornado or a bomb.
Wow, that's a great analogy.
When what you really needed was to see the faulty blueprints of the building itself.
And that is exactly where next-generation sequencing, or NGS, completely revolutionized the field.
The shift from biopsies to genetic sequencing simply cannot be overstated.
Because before NGS, sequencing genes was a nightmare.
Right. In the past, we had Sanger sequencing, which was incredibly slow and wildly expensive.
It read the genetic code one single letter at a time.
Yes. So if you had to check 34 different massive genes for a single patient, it would take months and cost an absolute fortune.
But next-generation sequencing completely changed the physics of the process.
It did. We can now take a single tube of blood, extract the patient's DNA, shear it into millions of tiny fragments, and sequence all of them simultaneously on a microchip.
So it's doing it all at once.
Exactly. And then a computer stitches all the overlapping reads together to form a complete picture of hundreds of genes at the exact same time.
It is massively parallel sequencing. So today, an NGS neuromuscular gene panel is the definitive first-line diagnostic test.
Yes, it's fast, it's non-invasive, and it provides an absolute molecular-level answer.
Usually.
Yes, usually.
But the text warns that even with NGS, the diagnostic landscape is still muddy because of something called a VUS.
A variant of uncertain significance.
Right. What is that exactly?
Well, this is the frustrating reality of modern genetics. When we sequence your DNA, we are reading a code made of billions of chemical letters.
Right.
And human beings are incredibly diverse. We all carry thousands of harmless spelling variations in our code naturally.
Just normal differences between people.
Exactly. So the NGS panel might flag a typo in the dysferlin gene. The computer says, hey, at position 402, there's a G instead of an A.
Okay, I found a typo.
But if that specific typo has never been recorded in any other human being before, the geneticist has a major problem.
Because they don't know what it means.
Right. Is that typo actually changing the shape of the dysferlin protein and causing the muscle disease?
Or is it just a harmless variation, and the real cause of the patient's weakness is hiding somewhere else entirely?
Exactly. That is a VUS.
It's like finding a typo in an instruction manual that says tighten the nut instead of tighten the bolt.
Right.
Does that typo cause the whole engine to explode, or is it close enough that the mechanic figures it out anyway?
That's the perfect way to look at it. And to solve a VUS, we sometimes have to go back to the old methods.
Like the biopsy.
We might finally order that invasive muscle biopsy, yes.
Yeah.
But this time, we aren't just guessing blindly.
You know what you're looking for.
Yes. We take the tissue and we apply a special chemical stain specifically designed to bind to the dysferlin protein.
And if the tissue glows under the microscope.
The protein is there and the VUS is harmless.
But if it's dark.
The protein is missing and we have caught the culprit red-handed.
That is so cool. And we also use advanced MRI imaging to hunt down clues, right?
Yes, muscle MRI is a huge part of the diagnostic process now.
And this isn't just looking to see if the muscle is physically small. The text details how certain genetic mutations cause fat to replace the muscle in highly specific, almost artistic patterns.
It's fascinating because water and fat respond differently to the magnetic pulses in an MRI machine.
So they look different on the scan.
Right. Fat shows up incredibly bright white on a T1 weighted MRI, while healthy muscle is a dark gray.
So in the collagen VI-related myopathies, the MRI shows a classic outside-in pattern in the vasty muscles of the thigh.
Yes. The bright white fatty tissue literally forms a ring around the outer perimeter of the muscle.
And then it slowly eats its way inward toward the center over the years.
Right. Seeing that specific visual signature on an MRI can give a clinician immense confidence in a diagnosis even before the genetic testing comes back.
Or it can help them confirm a tricky VUS.
Absolutely.
But when setting up these NGS genetic panels, Dr. Lulak makes a deeply urgent point about panel design.
A critical point.
The text insists, in no uncertain terms, that any panel looking for LGMD must also include the genes for congenital myasthenic syndromes.
EMS, yes. This is perhaps the single most important clinical takeaway for a practitioner reading this review.
Why? Because CMS is a completely different category of disease.
Entirely different. It is not a dystrophy.
Okay, so what's happening in CMS?
The muscle fibers themselves are structurally perfect. There's no necrosis, no tearing. The problem is at the neuromuscular junction.
The neuromuscular junction,
Yeah.
that's the microscopic gap between the end of a motor nerve and the surface of the muscle fiber, right?
Yes, it's the communication relay between the brain and the muscle.
Think of it like a car engine. In a muscular dystrophy, the engine block itself is rusting away and falling apart.
Right. But in CMS, the engine block is pristine. It's the spark plugs that are misfiring.
Ah, I see. So the nerve sends the electrical signal down the wire. It releases chemical neurotransmitters across the gap.
But the receptors on the muscle side, because of genetic mutations in genes like DOK7 or GFPT1, are deaf to the signal.
So the muscle never gets the message to contract.
Exactly. So the patient experiences profound weakness.
And the clinical trap here is that mutations in those specific CMS genes cause a pattern of weakness that exclusively targets the limb girdle muscles.
While completely sparing the muscles of the eyes and face.
Which means a patient with CMS walks into the clinic looking absolutely identical to a patient with LGMD.
Identical. You cannot tell them apart just by looking.
But the implications of misdiagnosing them are tragic.
Beyond tragic. Because true LGMDs, where the muscle structure is actually failing, currently have no FDA-approved pharmaceutical treatments that restore strength.
Right. You can only manage the decline.
But CMS, the broken spark plug, is highly treatable.
Wait, really? How?
We have simple oral medications like salbutamol or ephedrine that can chemically modify that neuromuscular junction.
They basically boost the signal.
Exactly. And they dramatically restore the patient's strength and function.
So if a doctor orders a cheap, poorly designed genetic panel that only looks for LGMD genes and forgets the CMS genes,
They will completely miss the DOK7 mutation.
they will just shrug, tell a patient they have an untreatable progressive dystrophy, and send them home to slowly lose their mobility.
When a simple daily pill could have fundamentally changed the trajectory of their entire life.
Wow. You absolutely cannot miss a treatable mimic.
You owe it to the patient to cast a wide genetic net.
And the biology actually throws one more massive curveball in this text.
Oh, yes. The pleiotropy.
Right. The review notes true pleiotropy in certain genes like PLEC and GMPPB.
Which means a single mutation in these genes causes both diseases simultaneously in the exact same patient.
So the structural plectin protein in the muscle wall is broken, causing the physical dystrophy.
And the receptors at the neuromuscular junction are malfunctioning, causing the CMS.
In those rare, unlucky cases, the patient is basically fighting a war on two fronts.
They really are. And treating the CMS component with medication won't cure the underlying structural destruction of the dystrophy.
Right, because the engine block is still rusting.
But it will maximize the efficiency of whatever muscle tissue they have left, which vastly improves their daily energy levels.
It's incredible. Which really brings us to the daily reality for the vast majority of patients who don't have a treatable mimic.
Living with LGMD.
Right. Because right now, today, we cannot fix the broken code. So how does a patient manage a body that is actively breaking itself down?
It requires a massive, highly coordinated, multidisciplinary effort.
It's not just one doctor.
Not at all. A neurologist monitors the overall disease progression. Physical and occupational therapists work to maintain mobility and prevent joint contractures.
Contractures which happen when the muscles shorten and essentially freeze the joints in place.
Right, and cardiologists and pulmonologists are actively monitoring the heart and lungs, ready to intervene with pacemakers or non-invasive ventilation when those systems inevitably begin to fail.
But the most complicated tightrope walk for the patient on a daily basis is exercise.
Well, absolutely.
Because we talked about the dysferlinopathy teenagers who destroyed their muscles by working out too hard.
Right, so physical therapists have to map out this really fragile Goldilocks zone of activity.
You have to move to keep your cardiovascular system healthy and to prevent your joints from locking up.
But you have to move in very, very specific ways.
So what's allowed?
Low-impact aerobic exercises like swimming in a heated pool or riding a stationary bicycle at a moderate pace. Those are generally safe and beneficial.
Okay, but what's forbidden?
High-resistance weightlifting. And crucially, eccentric exercises are strictly forbidden.
Let's really explain eccentric exercise because it is the exact motion that causes the most damage.
Okay.
An eccentric contraction happens when your muscle is actively generating force, but it is physically lengthening at the same time.
Right. Think about doing a pull-up.
Okay,
When you pull your chin up to the bar, your biceps and back muscles are shortening.
that's a concentric contraction.
Right. But when you slowly lower yourself back down, fighting gravity, your muscles are still fully engaged and under immense tension, but they are stretching out.
That is an eccentric contraction.
Yes. And just walking down a steep hill or a flight of stairs is entirely eccentric for your thigh muscles.
Your quads are acting as brakes, essentially,
Yeah.
stretching under the full weight of your body with every step.
And microscopically, eccentric contractions are brutal.
Why? What's happening inside the cell?
Deep inside the muscle fiber, the individual contractile units, called sarcomeres, are anchored by structures called Z-discs.
Okay.
During an eccentric contraction, those Z-discs are violently pulled apart. The mechanical shearing stress on the cell membrane, the sarcolemma, is exponentially higher than during any other type of movement.
Now, in a healthy body, that intense shearing stress causes microtrauma that actually triggers muscle hypertrophy.
Right. It signals the body to build more muscle.
But in a dystrophic muscle, whether it's missing the dystrophin patch kit or the alpha-dystroglycan anchor or the calpain-3 maintenance screw, the cell membrane simply shatters under that eccentric load.
The cell just dies.
So for an LGMD patient, something as totally mundane as carrying a heavy box down a flight of stairs isn't just tiring.
No, it is a molecular catastrophe.
They have to constantly monitor themselves for overexertion.
And the text lists the specific red flags patients need to watch for.
Like what?
Excessive muscle pain that peaks 24 to 48 hours after activity, severe cramping, and of course the dark urine signaling rhabdomyolysis.
It sounds like a daily, exhausting calculus just to exist.
It really is, which is exactly why the drive for therapeutics is so desperate and so intensely focused.
Because we know the exact genetic typos now.
Yes, we know exactly which biochemical pathways are failing.
So the ultimate goal is to just fix it at the source.
Exactly.
But developing these drugs is a monumental challenge. I mean, the first hurdle is just the sheer math of clinical trials.
The math is incredibly daunting. LGMD as a whole is already a rare disease.
But when you subdivide it into 34 distinct genetic types...
You are dealing with ultra-rare patient populations.
Right. And to prove a drug actually works to the FDA, you need a statistically significant number of patients enrolled in a double-blind, placebo-controlled trial.
Finding enough patients with the exact same genetic mutation at the exact same stage of disease progression is incredibly difficult.
And even if you find them, how do you measure if the drug is actually working?
That's another massive hurdle. The review strongly emphasizes the lack of validated clinical outcome assessments.
Meaning the tests we use to measure strength might be flawed.
Exactly. If you are testing a drug for a fast-moving distal myopathy that affects the calves,
Okay.
you might measure success by timing how long the patient can stand on their toes.
It makes sense.
But if you use that exact same test for a patient with a slow-moving proximal myopathy like calpainopathy, where the calves are perfectly fine.
The test will show zero change over 2 years.
Right. The drug might be actively saving their hip muscles, but the trial will be deemed a total failure because the test was wrong.
You essentially need a bespoke, custom-designed clinical trial structure for every single one of the 34 subtypes.
It's an astronomical undertaking.
But despite these massive hurdles, the science is actually moving.
Yes, there are bright spots.
The text highlights a phase 3 trial that is taking a really clever, non-viral approach for LGMDR9.
That's the alpha-dystroglycanopathy caused by the FKRP mutation.
Right, the sugar-coating one. And they were using a substance called ribitol.
Ribitol is a fascinating biochemical workaround.
How does it work?
Well, remember that in R9, the FKRP enzyme is mutated. Its job is to attach sugar chains to the alpha-dystroglycan anchor so it can stick to the matrix.
Right, and because of the typo, the enzyme is sluggish. It's terribly inefficient.
But, and this is key, it isn't completely dead. It still has some residual baseline activity.
Okay, so what is ribitol?
Ribitol is a pentose alcohol. It's essentially a naturally occurring sugar alcohol, and it acts as the raw material, the substrate, that the FKRP enzyme uses to build those complex sugar chains.
The strategy here is just brilliant in its simplicity.
It really is.
It's like if you have a lazy, inefficient factory worker, you don't fire them because you have no one to replace them with.
Right.
Instead, you dump a massive, overwhelming pile of pre-sorted parts right onto their desk to make their job as physically easy as possible.
That is exactly what they are doing. You provide a superphysiologic dose of ribitol flooding the body with vastly more of this compound than it would ever naturally encounter.
And by saturating the environment, you force the sluggish FKRP enzyme to operate at maximum possible capacity.
And preclinical studies in animal models have shown that this flood of ribitol actually works.
It boosts the residual enzyme activity just enough to successfully restore the glycosylation, the sugar coating of the alpha-dystroglycan anchor.
Stabilizing the muscle membrane.
It's an elegant therapy because you aren't trying to change the patient's DNA, you are just chemically optimizing the broken system they already have.
Exactly. It's relatively safe.
But ribitol only works because the enzyme isn't fully dead. What about the patients who are completely missing a vital protein, like dysferlin?
For them, the only true hope is gene therapy.
We are talking about viral vector-based gene replacement.
This is the absolute bleeding edge of medicine. And it is fraught with incredible promise and, frankly, devastating danger.
Let's explain the concept because it's straightforward in theory. You take a virus, typically an adeno-associated virus, or AAV.
Right.
You essentially hollow out the virus. You strip out all of its own viral DNA so it can't replicate or cause a traditional infection.
You just keep the outer protein shell, the viral capsid.
Because viruses are nature's perfect delivery vehicles, they have evolved over billions of years to be incredibly efficient at breaking into human cells.
Right. Once you have that empty viral shell, you pack it with a synthetic, perfectly healthy copy of the human gene that the patient is missing.
Say the CAPN3 gene for calpanopathy.
Exactly. You inject trillions of these engineered viruses into the patient's bloodstream.
The viruses travel through the body, find the skeletal muscle cells, bind to the surface receptors, and are swallowed into the cell.
They travel to the nucleus and unleash the healthy DNA.
And the muscle cell's machinery reads that new, healthy blueprint and starts manufacturing the missing protein.
The missing structural bolts are replaced, the sarcolemma is stabilized, and the dystrophy is halted.
I mean, it sounds like an absolute miracle.
And in mouse models, it looks like one.
But when we transition from a 20-gram mouse to a 70-kilogram human being,
The biology turns profoundly hostile.
the sheer scale of the problem is the barrier, isn't it?
It is. Skeletal muscle is the largest organ system in the human body. It makes up about 40% of our total mass.
Right.
To get the viral vector into enough muscle cells to actually stop the disease, you have to infuse an astronomical dose of the virus.
How much are we talking?
We're talking hundreds of trillions of viral particles per kilogram of body weight.
And your immune system is not just a passive observer in this.
No, it is not. It does not know that this virus is carrying a life-saving payload.
It just sees trillions of foreign viral invaders flooding the bloodstream all at once.
And it mounts a massive, overwhelming, violent defense.
The source material for this deep dive is remarkably and tragically transparent about this reality.
Yes. Dr. Lulek's text explicitly documents recent patient deaths in these clinical trials.
It specifically notes a patient death from severe liver failure in a trial for LGMDR5.
Right.
And it references multiple fatalities in trials for Duchenne muscular dystrophy using a gene therapy drug called D-landestrogen moxparvovec.
Particularly in older, non-ambulatory patients.
The liver failure is a direct result of the delivery system, isn't it?
Yes. The liver is the body's primary blood filter. It's packed with specialized immune cells called Kupffer cells.
So when you inject trillions of AAV particles, a massive percentage of them are just naturally swept up by the liver.
Right. The liver cells become choked with the viral capsids.
And then the patient's T cells, the assassins of the immune system,
They recognize the viral proteins inside the liver cells and decide the entire organ is hopelessly infected.
so the T cells launch a massive inflammatory attack, literally destroying the liver tissue.
Leading to acute organ failure and death.
These tragedies have forced the FDA and regulatory bodies worldwide to place clinical holds on multiple trials.
It has forced the entire neuromuscular community to agonizingly reevaluate everything.
The safety protocols, the immunosuppression regimens needed to try and hide the virus from the T cells.
And really just the absolute biological limits of the human body.
We spend so much time marveling at the genius of genetic engineering, but reading these case reports is a deeply sobering anchor to reality.
It is.
The scientists aren't just solving puzzles on a whiteboard. They are asking patients often young adults, who are watching their bodies slowly fail to take a drug that could cure them or could trigger a lethal immune storm.
The stakes are absolute.
How does a researcher or a clinician carry the weight of that risk?
It requires a profound level of ethical clarity and, frankly, resilience.
The editor's preface to this issue of Continuum, written by Dr. Lyle K. Jones, Jr., addresses this directly, doesn't it?
He does. He reminds the medical community that the arc of scientific progress is not a smooth upward curve,
No, it is a jagged line.
forged through moments of breathtaking discovery and moments of profound, tragic failure.
He writes about how easy it is for bad faith actors or public skeptics to point to these clinical trial deaths as proof that science is arrogant or failing or moving too fast.
Right. But he counters that skepticism with the harsh reality of the alternative.
Because the natural history of these muscular dystrophies is unrelenting.
For many of these subtypes, doing nothing guarantees a slow, painful decline into severe disability and early death.
Doing nothing is not a safe harbor.
No. The researchers owe it to the patients to maximize safety, to design better, stealthier viral vectors, and to demand rigorous oversight.
But they absolutely cannot stop trying.
Dr. Jones leaves the reader with a really powerful adaptation of a famous quote. He says, "If we give up, the fault will lie not in our genes, but in ourselves."
It is a mandate to keep pushing into the dark, despite the risks, because the patients are waiting.
Absolutely.
We have covered an immense amount of ground today.
We really have.
We traced the history from Walton and Nattrass trying to organize an overflowing bucket of diagnoses, all the way to next-generation sequencing microchips that read billions of letters of DNA.
We looked at how a tiny typo can tear apart the structural scaffolding of a muscle cell.
Blister the skin and destroy the kidneys.
And we've seen how precise diagnostics are fundamentally changing the way patients survive today.
Giving them the exact blueprint of their disease to help them navigate the really dangerous waters of exercise and management.
All while the scientific world races to build a safe delivery system for the ultimate cure.
Which leaves us with a final thought for you to carry with you.
As next-generation sequencing gets cheaper and faster, we are rapidly approaching an era where your DNA isn't a mystery anymore.
It's just another file in your medical record. We are all eventually going to peek behind our own genetic curtains.
And when we do, we are all going to find our own hidden typos.
Our own variants of uncertain significance. Think about what it means to hold a blueprint of your future health with all of its inevitable flaws.
And as you do, think about the immense, almost incomprehensible bravery of the patients participating in these first-generation gene therapy trials.
They're risking their lives, offering their bodies to science, and navigating the most terrifying diagnostic and therapeutic muddy waters in modern medicine to pave the way for the cures of tomorrow.